first start uploading, so you might have a pop-up to stay in the meeting. Okay, so the recording is on. And then let's also get started. So welcome to the NPA seminar. So normally I'm the one that hosts the heavy ion seminars, but for today we have a speaker that is otherwise also the host. So that's why I'm replacing him for being the host for today. Today we have Pranava Teja Surukuchi. I think that's pretty close to how one should say it. So and let me introduce him a bit. So he got his PhD from the Illinois Institute of Technology in Chicago in 2019. During his PhD, he worked on the Prospect reactor neutrino experiment, leading actually the design, fabrication, QA, and the assembly of the inner detector subsystems, and led its first sterile neutrino search. And he then joined us at the Wright lab at Yale as a postdoc, working on the Project 8 neutrino mass experiment and also CUORE, neutrinoless double beta decay experiment, while also continuing to work on the Prospect experiments. And then for both experiments, he is now leading efforts on the designs. And well, we will hear today about the results of the CUORE experiment. So that's very interesting. The seminar will be about 50 minutes, and then we'll have also time for questions and discussion. And yeah, as I said before, whenever I'm hosting the heavy ion seminars, we start with a quick roundtable of introductions so that the speaker knows his audience a bit better. This is especially nice when it's an outside speaker, but let's just also do that today. So I'll just start, and then we'll try to go on in alphabetical order of the first name. Might be a bit confusing because you're always on top yourself on the Zoom list, but that's a bit chaotic and also breaks the ice, so who knows. But I'll start. So I'm Mike, I'm a postdoc in the heavy ion group for the ALICE experiment at the LHC, and I work mainly on photon analysis. So I also hope to meet you in real life. It can probably happen soonish, right? So that's good.
That's hoping for it.
Yeah, so I guess I'm next alphabetically. So my name is Akko. I'm a fourth-year graduate student working with David Moore, also on neutrinos double beta decay with EXO 200 and EXO.
Hi, I'm Andy Shimkowiak. I always tell everyone that I'm an X-ray astronomer because that's what I was, but I feel particularly attached to this because back in the dawn of calorimetry, I was doing some of the early experiments on cryogenic calorimeters, and I've talked to a bunch of people about tellurium and stuff.
Hi everyone, I'm Dave Moore. As Akko said, we're working on EXO and double beta decay as well.
Hello, I'm Johnny, and I'm a postdoc working with the Sarah Demers in the Midway experiment and in the other experiment at LHC.
I'm Hannah. I'm a third-year grad student like Mike, also working on ALICE, and I predominantly study jets and heavy ion collisions.
Hi, I'm James. I'm an engineer here at the lab. I've worked with a lot of you, so my name should be familiar. And if it's not, I hope to work with you soon.
Hi, I'm Jay. I'm a postdoc working on cosine dark matter experiments and microneutrino experiment.
Hey, I'm Mike. I'm a postdoc working on axion searches with the haystack experiment.
I'm Penny Slocum. I'm working on Project 8 simulations at the moment.
Yeah, hi, I'm Raghav. I'm a postdoc in the heavy ion group working on star jets.
So now we would have Raina or otherwise Samantha.
Yeah, I'm Samantha. I'm a second-year grad student, and I also work on CUORE with Pranava and work with Karsten Heger and Reina Moriyama.
So now maybe Sierra, Thomas, or William.
Sure, I can go. My name is Tom Langford. I'm a research scientist with Karsten's group working on Prospect, Diabay, and dabbling in a few other things. So looking forward to the talk, Pranava.
Hi, I'm Will Thompson. I think I'm in order because I joined late, but I think I caught on to what's going on. So I'm a graduate student working with Reina Maruyama on the cosine 100 dark matter search.
Okay, great. Yeah, actually, the roundtable was quite efficient for this amount of people, so that's awesome. So now that we know everyone, let's go. So the floor is yours, Pranava.
Right. Yeah, thanks everyone. Thanks for those introductions and thanks for attending the talk. As the title says, I'll be talking about the recent results from the CUORE experiment today. So the obligatory standard model slide, we don't need to go too much into detail, but a couple of things to point out here. We have learned a lot about neutrinos in the recent past, in the last 20 years, primarily, especially from the oscillation experiments. And the oscillation experiments gave us a lot of details about neutrinos, but it also let us know that neutrinos are at least two of them are massive, but we don't know the actual absolute mass of these neutrinos. What we do know is that the mass of neutrinos are 5 orders of magnitude lower than electron mass from several experiments. We also don't know if neutrinos are Dirac or Majorana type. The smallness of the neutrino mass may actually be linked to the Majorana nature of neutrino via seesaw mechanism. And one way to look for Majorana nature, one of the best ways we know to look for Majorana nature is using double beta decay experiments. Before going into the neutrinos double beta decay experiments, let's look at the double beta decay. So in a double beta decay, 2 neutrons simultaneously convert into 2 protons, releasing 2 electrons and 2 electron antineutrinos. This is possible only for a few nucleus, even nucleus, where regular beta decay is energetically forbidden. And the half-lives of these are of the order of 10 to the 20 years. So just for a scale that's much, much longer than the life of the universe. There are 35 naturally occurring isotopes that are capable of undergoing double beta decay. And we have measured half-lives for several of these isotopes. Going on to neutrinos double beta decay, this is similar to the double beta, 2 neutrino double beta decay, but it is not discovered. So it's a hypothesized process. And if observed, it tells us a few things. It tells us that neutrinos are of Majorana type, and the lepton number is violated, and it could hint to the observed matter-antimatter asymmetry through leptogenesis. The neutrinos double beta decay experiments measure half-life of this process, or put limits on half-lives of this process. And through the half-life, we can constrain the neutrino mass and ordering. So the equation shown here is the half-life. And a couple of things to notice here is the half-life is inversely proportional to the square of the effective neutrino mass. So the smaller the neutrino mass is, the harder it is, the longer half-life is, and the harder it is for us to detect. And it also depends on phase space factor and nuclear matrix elements. And the uncertainty in the nuclear matrix elements are currently what drives the uncertainty in the conversion from measured half-life to the conversion of effective Majorana mass. This whole equation is under the assumption of light neutrino mass exchange. And so far, several experiments have placed limits on this effective Majorana mass. And though that's shown on the right plot here, this just about grazes the inverted hierarchy. And the next generation experiments, they want to go below the inverted hierarchy. And I guess just to give a reference, the inverted and normal hierarchy comes from the fact that, or inverted and normal ordering comes from the fact that we know the differences in mass, but we don't know the ordering in which neutrino 1, 2, 3 are ordered. The current limits are placed using multiple experiments using many isotopes. And it is important to place these limits using multiple isotopes because that reduces the systematic effects that one isotope or an experiment may see. So how do we search for neutrinoless double beta decay? In this process, unlike the 2 neutrino double beta decay, there's no neutrinos coming out. So all the energy is taken away by the electrons. So what we are essentially searching for is an anomalous peak at the Q value of the isotope. And in presence of backgrounds, neutrinoless double beta decay sensitivity depends on a few parameters. And so if you want to build an experiment, you want to have high isotopic abundance, either naturally or enriched. You want to have a very efficient detector. You want to have a huge detector, as big of a detector as you can have. So high mass. You want to run it for as long as you can. And the two other important things are backgrounds and energy resolution. So the plot here shows 2 neutrino double beta decay and neutrinoless double beta decay, and this is not to scale. But one can notice that if the backgrounds are high, this neutrinoless double beta decay drowns in the background. So we want to have very low backgrounds. And also we can see if the resolution is not sharp, if it's broadened, it will again be drowned within the backgrounds or 2 neutrino double beta decay. So we want to also have very sharp energy resolution for these experiments. So CUORE is one such experiment searching for neutrinoless double beta decay. And we are, the experiment is composed of collaborators from 4 different countries. I explicitly put a collaboration picture with people present in person with the hopes that the next collaboration meeting will be in person. All right, so CUORE stands for Cryogenic Underground Observatory for Rare Events. The primary goal of this experiment is to search for neutrinoless double beta decay in tellurium-130. The experiment is designed into towers containing crystals. So there are 19 towers, each containing 52 crystals, and so that adds up to 988 tellurium dioxide crystals. The size of this tower is roughly a meter long, and it weighs about the crystals. Some of the crystals, they weigh about 750 kilograms, which accounts to roughly 200 kilograms of tellurium-130. The goal of the experiment is to have low backgrounds of 10 to the minus 2 counts per keV per kilogram per year, with an energy resolution of 5 keV full width half max at the Q value. And the experiment is designed to have high efficiency with high duty cycle. Taking all these into account, with a 5-year runtime, the experiment is expected to have sensitivity to a half-life of 9 times 10 to the 25 years. And that, if we convert to effective Majorana mass, comes down to 50 to 130 milli-electron volts under the light neutrino exchange mechanism. The experiment is located in LNGS, which is an underground laboratory, and there is a mountain on top of the experiment, and that gives a very good natural shielding of roughly 3,600 meter water equivalent of overburden. And the lab, as many of you may know, hosts multiple other nuclear and particle physics experiments. The isotope of choice, as I mentioned, is tellurium-130. There are a few advantages with this isotope. It is naturally abundant, roughly making up 34% of tellurium. The Q value is relatively high. Most of the gamma backgrounds are below the isotope. So So we'll have a good way to look for this peak. And having a high Q value is also advantageous because the leakage from 2 neutrino double beta decay goes as 1/5 power of the Q value, and so having a higher tellurium or a higher Q value is better. So that helps. The isotope, as I said, is it's composed of, the crystals are composed of tellurium dioxide. So isotope is within the absorber, and these tellurium dioxide crystals were reproducibly grown with low contamination. So the technique used in the experiment is calorimetric technique, low temperature, so cryogenic calorimetric technique. The basic idea is quite simple. When energy is deposited in the crystal, the temperature of the crystal rises, and we have to instrument some sort of a thermometer to measure this change in temperature, so that we can infer the energy deposited. So each crystal it's a cubic crystal, roughly 5 centimeters, well, exactly 5 centimeters in size. And the crystals are maintained at 10 millikelvin, coupled to a heat sink through Teflon PTFE holders. The sensors we use are germanium neutron transmutation doped thermistors, and an increase in temperature in the crystal is seen as a difference in voltage across the NTDs. NTDs are short for neutron transmutation doped thermistors. We also have heaters instrumented on the crystal to perform gain calibration, among other things. The rise in temperature within the crystal is proportional to the energy deposited, but it depends on the heat capacity, and the heat capacity is proportional to the cube of temperature. So what this tells us is, the lower we get in temperature, the better delta T we see, the higher change in temperature we can observe in crystal. So we want to keep this at very low temperatures. So as a rough measure for 1 MeV energy deposition at 10 millikelvin, the rise in temperature is roughly 100 microkelvin. But eventually, if we can maintain all this, it gives a really good energy resolution. The response of this technique is independent of the energy, independent of the particle that is depositing energy in the crystal, at least in the way it's instrumented currently. But we also have flexibility in neutrinoless double beta decay isotope choice. So we can use, instead of tellurium dioxide, it's possible with this technique to use other material. So we can look for neutrinoless double beta decay in other isotopes as well. As I mentioned, the detector has to be kept at very low temperature. Not only that, it has to also have low backgrounds, as I already mentioned, and we also need to have very low vibrations, because vibrations can spoil the resolution of the detector. So for this reason, we have a cryogen-free cryostat, which is composed of nested cylinders, each defined by the temperature at which these vessels are kept. Up to the and these temperatures of the vessels go from 300 Kelvin all the way down to 10 millikelvin. Up to 4 millikelvin, these are cooled by pulse tubes, and past that, they are cooled by a dilution unit. As a rough measure, the total mass of the cryostat is 30 tons, and roughly 1 ton of that is kept at 10 millikelvin. So that's a reasonably huge detector that's maintained at very low cryogenic temperatures. So also I have a human to scale. You can see that the detector itself is not that big compared to a lot of particle detector experiments we think of. The backgrounds are kept low by using several methods. One of the things, as I mentioned, is natural shielding from the rock. This reduces all the cosmogenic backgrounds. We also have a lot of shielding around the detector, a lot of passive shielding. So this constitutes of lead, polyethylene, and borated polyethylene. And roughly 70 tons of lead is used, out of which 7 tons is kept at cold temperature. All this material has been very carefully selected, and the lead that's closest to the crystals, to the detector, comes from ancient Roman shipwrecks. So it's ancient lead where lead-210 has been decayed away. The copper we use is also very low radioactive copper. All the methods that were used in building, fabricating, assembling the detector are very carefully chosen to have very good radio pure detector. In addition to that, we use a few active background reduction techniques during the event selection itself. The development of CUORE experiment has taken roughly 30 years, starting in early 90s with a very small mass of 6 grams. And as I mentioned, now the detector is roughly 750 kilograms of tellurium dioxide. So here are a few photos to show the assembly and installation of the detector. And the installation of the detector has finished in summer of 2016. Well, assembly of detector has finished in summer of 2016. The cool down has started in December of 2016. And it took roughly a month for the cool down, with the first pulse detected in January of 2017. So the pulse shown here is the first pulse seen by CUORE experiment. So early on, there were a lot of optimization that had to be done to reduce noise in the detector primarily. I'll focus on a couple of things here. The pulse, we use 4 pulse tubes at a time to cool the 40 Kelvin and 4 Kelvin stages of the cryostat. And these are by default comes with the stepper motor from the vendor. That has been replaced early on by a precision stepper motor that is designed for low vibration. So the plot shown on the top right here is the temperature of a single crystal before installation of this precision motor versus after installation. And you can see that the changes in temperature has gone down after installing this precision motor. In addition to that, because we have 4 pulse tubes, we still see, even after installing these precision motors, we still see a little bit of noise in terms of changes in temperature in the crystal. So to reduce that, these pulse tubes, which run roughly at 1.4 hertz, are aligned in phase in such a way that some of this noise gets canceled. So the plot on the bottom right here shows a single channel, a noise power of a single channel before and after doing a phase optimization. And after doing a phase optimization, some of the noise cancels out, and you can see, especially for the harmonics of 1.4 hertz, the noise goes down. Right, and after these early optimization, there were still a few things that needed to be done early on in the first 2 years. So there was a lot of downtime. But after going through these a few hardware repairs, the overall downtime has gone down, and we have continued to take data starting in early 2019. And in the meantime, we have enhanced the data analysis techniques to improve our sensitivity. So after upgrades, as we continue to take data, we collected a lot of background data, so it's a lot of exposure. And the pie chart here shows that most of the the time spent by the detector is on taking background data. We have so far collected 17 data sets completely, and we have analyzed 15 data sets, which corresponds to more than 1 ton year of data, of tellurium dioxide data. And we are continuing to take data, as you can see on the plot on the right, where red is the analyzed exposure and blue is the total exposure that we have collected so far. So let's go through the analysis chain and see how the data we collect with these crystals can then be used for performing fits to neutrinless double-weighted decay. The data collected by CUORE is saved to disk, which we can use for offline triggering for all the data sets. We use this trigger called optimum trigger, and if the amplitude is crosses a certain threshold with an optimal filter, we trigger on the event. The plot shown here is the reconstructed energy when the trigger efficiency is 90% for all the channels within the detector. So you can see that for most of the channels, for most of the crystals, the reconstructed energy for 90% of trigger efficiency is about 10 kilo electron volts, and we place an analysis threshold of 40 keV, which includes 97% of all the channels with more than 90% trigger efficiency. We know that amplitude of the pulse is directly proportional to energy. So to calculate the amplitude, they are evaluated using an optimal filter, which is also used for the optimum trigger. And this optimal filter maximizes the signal to background ratio and helps us in reducing the thresholds and reducing the noise. So the plot here shows an average pulse for one of the crystals versus a filtered pulse. Once we have the amplitude, to be able to convert to energy, we need to make sure that we stabilize the gains. And the gain is, because the gain is temperature dependent, any small drifts in the temperature will be seen as change in amplitude. So we need to fix that. And the way we do it is using two different methods. One is using heaters that I mentioned early on, where the amplitude is measured as a function of baseline and fit is performed to that. And that can then be used to stabilize the amplitudes. Another way to do it is using calibration data. So the plot here on the right shows calibration data for thallium-208 peak, which is 2615 kilo electron volts. And we can use the fact that that peak remains at the same location and stabilize amplitudes as a function of baseline. And then that stabilized amplitude can then be used to convert to energy. And that is done using calibration. The calibration data is taken before and after each data set, and where each data set is roughly a month long, and calibration data set is roughly 3 to 4 days long. The calibration spectrum for one of the data sets is shown here, and you can see multiple calibration peaks. And the calibration peaks come from thorium-232 and cobalt-60 chains. And when we perform this calibration, these are independently calibrated. So we have each crystal being calibrated separately. After we get the energy, we need to perform.
One second. We have one raised hand from one of the audience, if that's fine with you.
Yeah, that's fine.
And go ahead, Raghav.
Yeah, hi. Pranava, I had a question on the previous slide, actually. Yeah, here. So I don't understand, what is this baseline actually? Baseline of what?
It's in regard to, I guess, this plot, it's just a arbitrary value that we have in measuring the voltage difference we have. So the way we measure
delta, right?
Right.
And why do you correct it to another arbitrary value? Apparently, it looks like at 5,000 something. I don't understand. Why is it not just flat at another value?
It's it's flat at 5,000 because that's just a chosen value, but we actually then use that 5,000 to convert that to the energy using the calibration peaks. So that specific conversion factor is as long as it is constant, is sort of irrelevant to the energy itself.
Right. Okay. So if I say I start with some like cobalt something, I can even put like, I don't know, 2,000, but then I will have a different correction factor to match that peak. Okay. Yep. Fair enough. Thanks.
Yep. Yeah. I was talking about the so once we have these the energy for each event individually, we want to place a few cuts, and one of the cuts is this anti-coincidence cut. Most of the backgrounds we see in CUORE experiment are typically multi-site events, or rather, most of the multi-site events we see in CUORE experiment are from radioactive contamination. And Monte Carlo simulation suggests that all the energy from one neutronless double beta decay event is contained within a single crystal, roughly 88% of times. And so for this analysis, we choose single site events to look for neutronless double beta decay. And this this helps us keep efficiency at a high value while still eliminating some of the main backgrounds like Compton scatters, surface alpha contaminations, and muons going through the detector. We also have another cut that we place to remove non-physical pulses. So I show an example of few pulses. We want to keep pulses that are physical and remove the ones that are not. And the way we do that is using principal component analysis. And this is done for each channel within each data set by treating the average pulse as the leading PCA component. And then a reconstruction error is built. A reconstruction error metric that's shown here is built, which quantifies the deviation of measured pulse from the expected pulse. So the reconstruction error as a function of energy is shown on the plot here, and two example pulses are shown on the right. And you can see that there is a very good agreement for a pulse that has low reconstruction error compared to one that has very high reconstruction error. So this reconstruction error is energy dependent, is slightly energy dependent. So we perform a normalization as a function of energy to have the same normalized reconstruction error value as a function of energy. And the PCA cut is then placed based on a figure of merit that is defined as signal to the square root of background, where the signal comes from the gamma peaks and background comes from the alpha region, which we use as the background proxy. Once we have that, we blind the data in the analysis chain. So the way we do it is by using this method called salting, where some of the events from thallium-208 peak, which is at 2615 keV, which is close to the Q value of tellurium, are shifted to the Q value of the tellurium and vice versa. And we perform fits on this blinded data. And then only when the analysis is finalized, we unblind the data. So the plot here shows in red the blinded spectrum where we have two peaks, one at tellurium Q value, tellurium 130 Q value, and one at the thallium-208 gamma peak at 2615. So once we do the unblinding, this is how the spectrum looks like. Here, it's over the full energy range from 0 to 6 MeV. And the spectrum shown here has base cuts, which are the low-level reconstruction and trigger cuts. And then as we apply more cuts, so AC is anti-coincident cuts and PSD is the pulse shape cut. As we place these cuts, the backgrounds go down. A couple of things I want to point out here is in the low energy region, the backgrounds are dominated by 2 neutrino beta decay. And we can see multiple peaks. And some of these peaks are from gammas and some of these are from alphas, but the region below thallium-208 peak is what we typically call gamma region, and above we call it alpha region, where above thallium-208 peak, all the backgrounds are primarily from alphas. Right, so once we have the spectrum, to be able to perform a fit, we need to understand the response of the detector well. And the response is modeled using thallium-208 peak at 2615 in the calibration data. So the main peak is characterized by 3 Gaussian peaks, and an additional few components are taken into account while performing this fit. And these components are flat background, multi-Compton spectrum, and X-ray peaks. So once this fit is performed, over a full tower. So I mentioned there are 19 towers, and this fit is performed 1 tower at a time to increase the statistics for the fit. And like I mentioned, this is all done with calibration data to make sure that there is no bias in the physics data. We take that line shape and scale it to other peaks in the physics data. And that tells us the bias as well as the resolution scaling to the Q value of tellurium 130. So the resolution with calibration data at 2615 keV is 7.78 keV, and it agrees very well with the full width half max at the Q value in the physics data. And we also see very little bias in the Q value. And the plots here show a fit to one of these peaks, and the resolution scaling as a function of energy using multiple peaks, and the energy bias as a function of energy. Right. We also need to understand the efficiencies very well. These efficiencies we divide broadly into 3 different categories. One is containment efficiency, which is the probability of neutrinoless double-weighted decay depositing all its energy within one crystal, and that is done using Monte Carlo simulations. And then we have reconstruction efficiency, which is low-level efficiencies, which are trigger, event reconstruction efficiencies, and pilot identification. And these are done using heater that I mentioned early on. We also have higher level efficiencies, which we do using background data at a dataset level. And I'll go through a couple of these. For the anti-coincidence efficiency, which is the probability that we correctly identify single site events, we take potassium 40 peak, and we look at the fraction of events that pass the anti-coincident cut to the ones that pass just the standard low-level analysis cuts. And we use potassium 40 because we don't have any other correlated events with potassium 40, so it's a relatively clean peak. So the plot here shows for one data set, potassium 40 energy distribution and the signal region we use, as well as the flat background region that we use to extract this anti-coincidence efficiency. We also calculate efficiency for the pulse shape discrimination. And this is the probability that a good physical pulse passes the PCA cut. And this is evaluated similar to the anti-coincidence efficiency, but we use multiple peaks here, which are potassium 40 and 2 peaks from cobalt 60 and thallium 208. And the overall efficiency comes from a combination of these 4 peaks. The method that we use for this particular analysis has been modified from the last analysis. The last analysis, we used this 6-parameter way of looking at the pulses, and we called it PSA cut. Now we use this PCA efficiency, and we have noticed that the PCA efficiency increases, PCA cut increases the efficiency by a few percentage. This not only helps in having better efficiency, but it also actually have higher efficiency at lower energies, which also helps in multiple other things like looking for two neutrino double beta decays, measuring the two neutrino double beta decay spectrum. So overall, the efficiencies, the total analysis efficiency is 92%, excluding the containment efficiency. And I want to just give a shout out to the two grad students here at the Wright lab at Yale who have worked on calculating these efficiencies for this data set. So that's Ridge and Samantha. So if you have any questions, you can reach out to them. Finally, so we have all of these information in hand and we want to perform a fit. And the way we do it is using unbent Bayesian fit over all the data sets using this toolkit called Bayesian Analysis Toolkit, or BAT in short. And the fit region we use is 2490 to 2575 keV. The plot shown here is the blinded energy spectrum in the fit region, in the region of interest. And the two peaks we see here are cobalt 60 sum peak and the peak at Q value that comes from the blinding where we take events from thallium 208. The parameters that we use in fit are decay rate, which is which characterizes the height of this peak, the amplitude of the cobalt 60 peak, the background index, so the background value, as well as the slope of the background. And we have a few other systematics. I'm not going to list them, but we implement them as nuisance parameters. So with all of this in place, we performed a fit to the 1 ton year of data, and we don't find any neutrinos double beta decay, but we place limits on the best fit rate, limits on the rate of this process, as well as the half-life of the process. And the half-life is placed at 2.2 times 10 to the 25 years at 90% credible interval. And when we perform the fit without any neutrinos double beta decay component, we get a background index of 1.49 times 10 to the minus 2 counts per keV per kilogram per year. We also calculate sensitivity using Monte Carlo simulations by generating 10,000 toy experiments, assuming no signal. And then we perform a fit using signal plus background. And the median sensitivity was found to be 2.8 times 10 to the 25 years at 90% credible interval, which corresponds to a probability of, if we compare that to the CUORE limit, that corresponds to a probability that CUORE limit is, there is a stronger limit than CUORE at 72%. So it is in a decent agreement with the expected sensitivity. So we have the half-life now, as I mentioned, we can then use to convert that to the effective Majorana mass limit using light neutrino exchange. And the value we have, the limits we place are from 90 to 305 milli-electron volts. And the uncertainties in this value, so the plot here, the uncertainty band in yellow comes mainly from the nuclear matrix elements. And I will remind everyone that the sensitivity for CUORE experiment with assumption that it will run for 5 years is at 9 times 10 to the 25 years with a limit on effective Majorana mass of 50 to 130 milli-electron volts, which is also shown on this plot in the blue color. I also show a different limits placed by several isotopes, and they're all competitive values currently. So let's move past and look at what we have measured so far and what we can do better. I have previously already mentioned below 2615 keV, the backgrounds are composed of gammas as well as alphas, but past 2615, it's mainly composed of alphas. So we call this alpha region. When a fit is performed to this region of interest, which is composed of gammas and alphas, we find that the background index there is almost equal to the background we see within the alpha region. So that is shown in the bottom plot here. So for different data sets, when we look at the backgrounds in the region of interest, which is composed of gammas and alphas, and in the alpha region, which is only composed of alphas, they are very similar to each other. And so that indicates that the backgrounds are primarily dominated by alphas, even within the region of interest. And in addition to that, the next set of backgrounds are expected to be muons that are the dominant background once we somehow, if we can get rid of the alpha backgrounds. So the next step for CUORE, this cryogenic method is CUPID experiment, which stands for CUORE Upgrade with Particle Identification. This is a collaboration with multiple people from 7 different countries. And the basic idea is quite simple. It's similar to CUORE, but with an upgrade. The measurement in CUORE is heat. So energy deposition is measured as heat. For CUPID, the plan is to measure heat as well as light. Heat is independent of the energy, independent of the particle depositing the energy, whereas light yield depends on the type of the particle that is depositing the energy, and we can use that to discriminate alphas from the gammas and betas. And the plot shown here is one of the demonstrators for CUPID called CUPID-MO, where discrimination between gammas and alphas are shown. The plans for CUPID are to use the same CUORE infrastructure, the cryogenic infrastructure that CUORE uses, which is quite successful, and to use 1600 lithium molybdate scintillating crystals, which roughly gives 250 kilograms of molybdenum 100. The Q value for molybdenum 100 is higher than tellurium, so some of the backgrounds will be reduced just from the fact that we are moving away from the gamma background region. And we also employ active discrimination to reduce other backgrounds. The CUPID-MO collaboration has demonstrated the use of lithium molybdate crystals with good energy resolution and really good discrimination. And the plan is to have muon veto system for tagging muons, which is the next dominant background after alphas. So I want to also briefly mention that the work we have been doing primarily at Yale for this muon veto system, we have the plan is to have this muon veto system around the cryostat. The requirements here are to have high spatial uniformity and good efficiency, but it also gives us tight spatial constraints. So the plan is for us to have a modular design using plastic scintillator, wavelet shifting fibers, and scintillating and silicon photomultiplier as the sensors. We have ongoing prototyping at Wright Lab. I show a few photos with scintillator panel that's been machined, and there's a scintillating wavelet shifting fiber going through the panel. One of the silicon photomultipliers, as you can see, it's quite small, and fully assembled prototype with scintillator, wavelet shifting fiber, as well as silicon photomultiplier where we take data. And if you have any questions, reach out to Samantha and Iris, who have been working on the prototyping efforts. So it's the shout out to Samantha and Iris as well. So finally, taking all this into account, if we reduce alpha backgrounds and muon backgrounds, and assuming that we'll be using 250 kilograms of lithium molybdate and run it for 10 years and get good energy resolution as well as reduce the backgrounds, the expected baseline sensitivity with CUPID is going to be 10 to the 27 years, which will cover the inverted ordering as you can see here, where the limits can be placed from 12 to 20 millielectron volts if we assume light neutrino exchange. So in conclusion, CUORE is the largest ultra-cryogenic calorimeter searching for neutrinous double beta decay. We have taken data since 2017, but we have been stably taking data since 2019 with roughly at a rate of 50 kilogram years per month. We have already analyzed more than a tonne-year of data and placed limits on half-life for tellurium-130 and effective Majorana mass. CUORE has already demonstrated good energy resolution and background reduction, and the next phase of CUORE Cupid will be able to perform one of the most sensitive searches for neutrinous double beta decay. With that, thank you all for attending, and I'll be happy to take any questions.
Yeah, thank you for your interesting talk. Yeah, so let's open the floor for questions. You can either raise your hand or just unmute and ask. So go ahead.
Maybe I'll ask one question. So it's very interesting talk overall, Pranava. So
thank you.
So you showed a lot of preliminary results, right? So you had for all the data that you've taken so far and you've analyzed. So just I don't know how this is happening in this community, but like when we go from preliminary to the paper, there's some typical additions or some further systematics or something like that happens, right? So can you tell me what is going to show up in the publication, or are you waiting for more data, something like that?
Yeah, so we already have these results on archive for a couple of weeks, maybe 3 weeks, I think.
Okay, all right.
And we have submitted it to a journal, and the plan is that we don't call it preliminary once it's been peer reviewed. That's the whole idea. So
okay, so it's still preliminary, right, until it's published.
Right, exactly.
Okay.
So we don't really expect anything to change unless there are some big questions from reviewers, which I don't think is a possibility.
Yeah.
But yeah, the idea is it's preliminary until it's published.
Got it. Okay.
I see Will.
Yeah, either one of you two go ahead with
Okay.
your question.
Yeah.
Maybe Giantonio was first, I think, with raising his hand.
Oh, sorry, I should not take the host responsibilities.
It comes naturally.
It's okay.
Right?
That was a very nice talk. And yeah, I mostly had a couple of curiosity to ask. So on slide number 40, you showed a plot with some efficiency values, and I was curious on the bottom left plot, like why there are some points with the extremely small uncertainty and others instead with the pretty larger uncertainty. So I was just curious to understand the origin of that difference in the error bars.
I think that just comes from the amount of data corresponding to
so it's really statistical uncertainty.
Yeah.
And also, yeah, that similar question was on slide number 43, I think, because there was the point. I mean, they're all very small, but the one on the right is particularly larger than the other. So I was thinking if it's a systematic uncertainty or is just statistically limited.
It is very statistically limited. So we collect a lot of potassium-40 compared to thallium-208. For example, potassium-40 is this peak, which has the smallest uncertainty. Thallium-208 has much fewer events, so we have much bigger uncertainty.
Okay, cool. And also then on the, sorry, very last, but then on the summary table, on the summary table of the efficiency here, these are just statistical uncertainties, or they include some systematics?
No, these include systematics. So I mean, these are all dominated by statistics, but we actually take systematic uncertainty into account as well. We use the systematics. I don't specifically mention here, but we use systematics. This is
I see. Yeah.
I don't explicitly mention the systematics, but we use them in FITS as nuisance parameters.
Cool. Thank you.
William?
Hey, great talk, Pranava. So I had a question actually about the muon veto system for Cupid. So, well, I guess CUORE and Cupid. I guess I'm wondering, what are you doing currently to veto muon events? And I guess what is it about the new experiment that is sort of necessitating the existence of a dedicated veto? Is it more background, or is there some difference in design that makes them harder to deal with?
Yeah, so I may actually have a backup slide on some of this. So yeah, so this is, I guess, one example where I can briefly mention. So the backgrounds we have currently are very dominated by alpha events, degraded alphas from the crystals and the material that makes up the towers. And with Cupid, we are going to remove these backgrounds by using pulse shape discrimination using scintillating bolometers, right? So we get rid of all the alpha backgrounds. And then what we are left with, especially at 30-34 keV, where we don't have any gamma backgrounds, are primarily muons. At the level where we are at with CUORE, muons are not a dominant background. So we don't, it's not a concerning limiting factor. That being said, we also, I think I mentioned here, we also apply this anti-coincidence cut, right, which removes all the events that have more than energy depositions in more than one crystal. So most of the muons that, first of all, there are very few muons at the underground. And the ones that go through the detector are going through, typically they go through multiple crystals. So we get rid of those. And after all of that is done, we are left with very few muon events. And that becomes a dominant background only once we can get rid of the alphas, which is the plan for Cupid, which is why it's more important for it for us to have efficient muon veto system for Cupid.
Do you have like a rough idea of how many of these events, or how many of these muon events would be single hit? Because it seems like just from the geometry, most of them would be multiple hit.
Yeah, so I don't have a number off the top of my head of the number of single hit events, but the muon background expected if we use single hit events after we get rid of the other backgrounds is 10 to the minus 4 of the order of 10 to the minus 4 counts per kilogram per kV per year. So that's 2 orders of magnitude lower than what we currently have, the measurement we have, which is, I guess, that's a good plot. So that's roughly 2 orders of magnitude lower.
Yeah. Okay, thanks.
Akko, go ahead.
Yeah, hey, thanks Pranava for the nice talk. I also had a question about the muon veto system. And so for Nexo, we've been interested in SIPMs. And for us, the requirements are very stringent. So I was wondering, for you, like the first question is, what's the wavelength of your scintillator? And are you able to buy SIPMs off the shelf that meet your requirements, or did you have to have like, specific development to meet your,
Yeah, so I mean, if we compare the requirements that you have, we have much less stringent requirements, right? Because the plan is for us to have this outside the whole cryogenic atmosphere. The wavelength is optical wavelength, right? So it's just we can buy SIPMs from just one of the well-known vendors like Hamamatsu is what we are currently working with, and those will provide us with enough efficiency in the wavelength that we are looking at, and the dark counts are low enough that we should be able to we should be able to live with it. We don't need to do any more R&D for SIPM development ourselves. What we are working on is to try to make it all work within the given constraints that we have.
I see. And what's the purpose of the wavelength shifter then, if the wavelength is already in the visible spectrum?
Yeah, so the wavelength shifter, the main purpose is to make the light collection uniform across the panel. So the plan is that the idea is that the light from scintillation is collected by the fiber that is then routed to the CPUM. So we can have big panels without losing all the light from reflections, loss in reflections. And because the CPUMs are really small, we need to be able to guide the light properly to the CPUM. So wavelength shifting fibers do the job of shifting or guiding the light, collecting the light efficiently across the panel and guiding it to the CPUM.
I see. Okay, very nice. Thank you.
I have also one question myself. At my old institute at NICAV in the Netherlands, there is still a group of people working on the xenon and tonne experiment. Could you maybe say a few words about what the differences would be in a few years, maybe, or what you hope to achieve or complement, or anything with respect to that experiment?
Could you mention the experiment again? I missed that part.
Xenon and tonne.
Oh, xenon and tonne.
Which I think is the detector setup is quite similar, right?
Not quite, right? So this is the scintillating for Cupid, at least it's the scintillating bolometer, right? For xenon and tonne, it uses xenon as the name suggests. And the differences are yeah, I'm trying to think of the similarities here. I am not aware of the top of my head if how well xenon one-tonne would be able to place limits on neutrinos double beta decay. I don't recall reading any, at least in the recent times, any limits from xenon and tonne experiment. I'm sorry, I don't actually have a good answer to your question. I cannot think of a way to answer that.
Oh, well, that's fine. I was just curious. It's okay.
Yeah.
Okay, do we maybe have someone else with the last question? We're nearly running out of time, but we would have time for one other question. Seems not, but we already had a few questions, so that's nice. So then I propose to then close the seminar here. So thanks again for this nice talk.
Thanks, and well, thanks everyone for the questions, and thanks for hosting.
Okay, then bye-bye to everyone. I'll stop the recording.